Here we are. We're going to finish nuclear energy with this last note from chapter 19 in our textbook, looking at the actual quantity of energy that's stored up within the nucleus and how that can be harnessed and used. So again, massive topic. So I want to spend a little bit of time today just kind of wrapping this all up and looking at the uses of nuclear energy, that energy that's stored up in the nucleus of atoms. So Einstein, at the beginning of the 20th century, in all of his brilliance, had lots of ideas that he believed to be true, none of which were testable. So he just kind of worked them out in his own way, in his head, on paper, on his chalkboards, on whatever he was working on, and he tried to rationalize and tried to explain the universe in ways that perhaps had never been thought of before. And he discovered a lot of things that ultimately turned out to be true, even though a lot of them couldn't be tested until long after he was dead. But he was brilliant. He was brilliant at the time. He was recognized for his brilliance at the time, and even today, I would say probably more so than even when he was alive. So one of the things that he looked at was, if we know that energy is conserved in chemical reactions, all right? So you learn this in grade 11 chemistry, you learn this in grade 12 chemistry, and we've learned from earlier parts of the course that thermal energy can be transferred from one object to another, and we have talked about the conservation of mechanical energy. So we have kind of precedent here that energy can be conserved. We also have this idea that if we start with 100 grams of reactant, we'll always end up with 100 grams of product. So Einstein was kind of, I can't attempt to understand how his rationale worked, but he came up with this idea that energy and matter, even though they, we had originally said that they cannot be created or destroyed, but forms of energy can be interconverted, and matter we know can be interconverted by breaking chemical bonds, even though we can't until this week, in our understanding, get rid of elements and atoms. We now have a way to look at Einstein's law of conservation of mass and energy. And it was all based upon his idea that if there is matter in the universe and there is energy in the universe, who's to say that they're not really two different forms of the same thing, like water and ice, that are very, very different, but that are interconvertible. And that was where E equals mc squared comes from. So on the left side here, I've got a quantity of energy, which is going to be measured in joules. On the right side of this equation, I've got the mass that we're going to be talking about converting into energy, and that's measured in kilograms. And c, as we know from physics, is the speed of light. 3.00 times 10 to the power of 8 meters per second. Okay, and what that does is it allows us to convert a quantity of mass into energy in joules. Now, the law of conservation of mass energy basically says that in an isolated system, I can interconvert matter and energy, right? But the total amount of the equivalence of these two will be constant. All right, so if some matter disappears, it will be converted into energy, but I can account for the mass that's disappeared in terms of the energy that's there. Now, nuclear reactions typically happen in very small quantities, and we typically think of them at the actual level of a single atom. It makes life a lot easier when we're trying to understand these things. So instead of talking about grams and kilograms, we often talk about our masses in nuclear using atomic mass units, right? Where an atomic mass unit is 1/12 of the mass of a carbon-12 atom, right? So it really represents the mass of a proton, which is equal to the mass of a neutron. Even though they're not totally identical, for all intents and purposes, this will work. So if I take the mass of a proton, take the molar mass for carbon and divide it by 12, I can come up with the mass of a single atomic mass unit, which is this number here. And instead of measuring our quantities of energy in joules. Again, a joule would be like having apartment buildings, or trying to get yourself a sample of something out of something that is absolutely huge, huge, huge. So the units of joules don't make a lot of sense when we're talking about energy at the single atomic level. So we actually have got a small unit called the mega electron volt, which is a quantity of energy. It's a quantity of energy that's carried, and it's the basic unit of energy within the nuclear world. Now, so things get a little bit kind of strange here, just like we talked about some strange things in our 19.3 note when we talked about changing elements into other elements and alpha decay and beta positive and beta negative emissions and gamma rays and all that. Things get a little bit kind of interesting here too, in that if I know what the mass of a proton is, okay, so let's say I know the mass of a proton, which I do know, and let's say I've got an atom of helium. So helium, so the helium, if I'm trying to find the mass of helium, the mass of a helium atom, not sure why this is not working for me here. Try one more time. Mass of a helium atom, it should be equal to the mass of 2 protons plus twice the mass of a neutron, because a helium atom has mass of 4, because it should have 2 protons and 2 neutrons. So I'm going to have to add to this 2 times the mass of a neutron. Plus I know if it's got 2 protons, I'm going to have to add twice the mass of an electron. Okay, and if I add all 6 of these particles together, a strange thing happens. Right? The mass of all the parts of an atom is actually higher than the mass of the atom. You think, okay, no, the sum of anything has got to be equal to the sum of its parts. Okay, so here we go. The sum of the parts is higher than the sum of the atom. You think, well, how is that possible? Where is the missing mass? If I've put this much mass into the atom, where did that mass go? Well, that mass is, as we might want to call it, a defect. It's actually called the mass defect. Okay? It's the missing mass in an atom based upon what I think the atom should weigh, what the mass should be, and what the atom actually has for a mass. So that missing mass is called the mass defect. I think, well, so where did the mass go? Well, that mass that's missing, based upon what I think should be there, has actually been converted into energy using Einstein. So if I can look at how much mass is missing from my atom, right, and then multiply it times the speed of light squared, it will give me an answer in joules, or if I'm using mega electron volts and mass in atomic mass units, I can calculate the amount of energy that's holding that nucleus together. Right? It's potential energy that's stored in the nucleus. Okay, potential energy stored in the nucleus. That's why when we break a nucleus apart, right, it releases that energy. Just like, again, giving an object a rock sitting up on a cliff has got gravitational energy that it can give up. There's energy stored up in this nucleus, just like the energy of that rock on the cliff, and that energy has been derived because of the mass of the particles having given up some of the mass and converted them into energy to hold them together. So the energy that holds the nucleus together is called the binding energy, and ultimately the binding energy is what I would need to add to an atom to break all of the nucleus apart into its individual separate nucleons, the neutrons and protons. So let's have a quick look here. In our textbook, we've got example 6 on page 645. It says when a helium nucleus is created from isotopes of hydrogen. Its mass is 0.018 units, atomic mass units, less than the mass of the particles that were put together. So if I take an H2 and an H3 and put them together, I should get helium-4 and a neutron that's kicked out. Right? And in doing so, there it is there. If I take an H2, I didn't even realize it was there. If I take an H2 deuterium and an H3, which is even a heavier isotope of hydrogen, notice that this first one has one proton and one neutron. The second one has one proton because it's hydrogen plus 2 neutrons. So what I've now got is a total of 3 neutrons and 2 protons. Well, here are my 2 protons here, and then my 2 neutrons are here, and then that extra neutron disappears. But if I was to take the mass of this helium atom and this nucleon, this neutron that was kicked out of the nucleus, the mass would be less than the mass of the particles that I started with. Okay, and then say, well, where did that energy, how did that energy arise? Well, it arose because some of the mass got converted into energy. So, if I want to figure out how much it is, it says the mass defect in this reaction, and again, the textbook goes into how this would happen, but basically, if I have 4 kilograms of helium, remember the molar mass for helium is 4.00, so its atomic mass unit would be 0.018, so we just make the equivalents in kilograms. So the mass defect in this reaction is 0.018 kilograms, so if I wanted to calculate how much energy is going to be released in this reaction, right, the question says how much energy is going to be released. There's my 0.018 kilograms times my speed of light. .00 times 10 to the 8th meters per second, quantity squared, and I'll get an answer which is 1.6 times 10 to the 15 joules. Okay, 1.6 times 10 to the 15 joules. Okay, that's from 4 kilograms. 4 kilograms, a bag of milk, right? A 4-liter bag of milk has a mass of about 4 kilograms. So if I had about that much helium, I could get that massive amount of energy, right? It says this quantity here is about 0.1% of the electrical energy used in the entire country of Canada in 1 year, right? So basically 1,000 times more than this is how much I would need for the entire country for an entire year. So that's a massive, massive amount of energy, right, coming from that nuclear fusion reaction. Now, I'm going to leave you with these questions here, but I'm not done with you yet. Okay, there's some questions on page 664, and you can look at doing the calculations. Okay, so I will leave you with those ones for now. Okay, I want to move on now, and I want to look at fission reactions in general, because they're the ones that we use in nuclear reactors, and they're also the ones that are have the potential to be used in nuclear weapons. Now, if I look at what my fuel is for a nuclear reactor, right, my fuel is basically going to be some type of large radioactive nucleus, right? The most common one probably is uranium-235, and it's unstable. It's radioactive. It will decay on its own if I leave it, and it's got a half-life, I can't remember, something like 1,800 months, I believe. Hang on one second. I think I remember it being down here. Uranium is 18 months. Okay, so about a year and a half. Okay, so I start with uranium, and it will decay on its own at a rate with a half-life of 18 months. So after 18 months, half's gone, a year and a half. After 3 years, 75%'s gone. After 4.5 years, 87%'s gone. After another year and a half, 6 years, I'm up to 92%'s gone. Right, so after 6 years. So it will take a while for it to disappear. However, we've discovered that if we fire neutrons at these uranium atoms, what happens is the atom, the nucleus, absorbs the neutron and becomes a uranium-236. Still uranium, because it still has 92 protons in the nucleus, right? And it will now have an extra neutron, giving it an extra unit of mass to make it a uranium-236. Highly, highly unstable. And what's going to happen is almost instantly it's going to fission. It's going to crack and split apart into two smaller nuclei. It's not just giving off an alpha particle now, it's actually going to smash itself into two particles. They're not always going to be krypton-92 and barium-141. There's a number of different possibilities. We'll see some of them in a minute. But notice that I've got here 36 protons and 56 protons. So I still have my 92 protons that I started with. And then I've got, uranium had 143 neutrons. Make this a bit bigger here, it might write better. Okay, my uranium had 235 minus 142, so that's 143 neutrons. And I'm going to add another neutron to it, which is right here. And then ultimately, so that 144 neutrons, 143 plus 1 makes 144 neutrons. If I look on the right here, krypton has 92 minus 36, which is 56 neutrons. And barium has 141 minus 56, which is 135, 85 neutrons. So 85 and 51 is 136. Oh, I'm still missing some. Hang on a minute. 92 minus 36. Oh, it's 56, sorry. Looks like a 91 there. So I've got 56 plus 85. That makes 91. That makes 141. Plus, I've got 3 lone neutrons that are going to be ejected. So all of my protons are accounted for. All of my neutrons are accounted for, all 144 of them, right? And what's going to be released here along the way is a massive amount of energy. Okay, now, where are those 3 neutrons going to go? Well, they're going to do exactly what happened up here a minute ago, which is they're going to, as they come off this reaction, they're going to slam into neighboring uranium-235s, and they're going to cause them to shatter and give off their 3 neutrons. And then these 3 new neutrons, so the first one made 3. Each of those 3 should become 9. Each of those 3 will make it to 27. The next, those 27 will make 81. So you can see the next reaction will make it 243, right? Then 729. So we just keep increasing our number of neutrons, and ultimately this can be very bad because the reaction gets faster and faster and faster and faster, and it gives off this, right? It just keeps giving off more and more and more and more energy, and that's a very bad thing because ultimately that's how our nuclear explosions happen. Now, it turns out that the textbook uses an example that I don't remember seeing before, but I really like it. It says the neutrons are traveling very, very fast, right? And in order for them to get absorbed by a neighboring uranium-235 to cause it to fission, I actually have to slow down the neutrons, right? They're going too fast. They use the example of skipping a stone on the surface of water. And when you throw that stone and it bounces and bounces and bounces and bounces, and it slows down every time. It bounces a little less each time until it gets to a point where it sinks into the water. The neutrons are the same. If they're going too fast, they can't be absorbed by the uranium atoms. So we actually have to slow them down, right? We have to moderate them. Now, it turns out that when we do this, the two that will slow down will ultimately be absorbed by new uranium atoms. So here's my original uranium atom, and I'm going to hit it with a neutron coming in up here. Okay, so here's my uranium atom, and I'm going to hit it with this neutron. It's going to break up into its barium and krypton, and it's going to fire off 1, 2, 3 neutrons. 2 of those are going to get slowed down, and they're going to get absorbed by the next uranium atoms. And it's going to break up into, this one's going to break up into an antimony and a niobium atom. But again, you'd see that the conservation of protons and neutrons happens, except 3 neutrons are kicked out again. And of those, 2 of them get slowed down. 1 of them basically just ends up getting fired out of the reactor. It needs to be absorbed, and we'll talk about how it gets absorbed by the moderator. The moderator will actually absorb all that energy. And then these 2 will hit 2 more uranium atoms. Right? So this one sends out its 2 neutrons to hit 2 more. These ones send out neutrons to hit more, and they send out neutrons to hit more, and this thing should hypothetically continue to grow until it is an explosive release of that massive amount of energy. Okay, the textbook says that the energy released in nuclear processes is 7 million times higher than an equivalent mass of dynamite. Right? So that's how much energy we are storing in this thing. And not only are we releasing a huge amount of energy, but we release it almost instantaneously. In less than 1 microsecond, right? 1/1,000,000th of a second, I'm going to release that massive amount of energy. Right? So that's the power of this type of nuclear process. But I don't want that to happen in Pickering or in a Bruce nuclear reactor, or in the Chalk River nuclear reactor, or even the McMaster nuclear reactor, because Mac has its own. It's the only private institution, it's the only university facility in Canada to have its own nuclear reactor. So I can't let this happen. So what we're going to do in our nuclear reactor, there's one more term I need to mention here, that the term is critical mass. The critical mass, so in order for this reaction to continue, I need to have enough uranium-235 in the fuel in order for it to continue. Right? And that's called the critical mass. So it's the minimum amount of nuclear fuel, uranium-235 in my sample, required for a chain reaction to continue. Okay, so let's look at the nuclear reactor now. In the nuclear reactor, we changed the way the moderator works such that it only moderates or slows down 1 neutron that's coming from that uranium fission reaction. So that means when 1 neutron hits it, it releases only 1 slow neutron to hit 1 more uranium, which will release 1 slow neutron, which will hit another uranium atom. And what that means is the rate of this process continuing, this chain reaction that's going on, happens at a constant rate, right? Because as 1 goes in, 1 comes out. As 1 goes in, 1 comes out. Before, when 1 went in, 2 potentially fissionable neutrons will come out, right? And then it causes the reaction to escalate. But we don't want that to happen in our reactor. So in order for the reactor to work, I need to have a moderator that's going to be able to absorb the energy of the electrons and the neutrons and slow down 1 neutron from each fission reaction. Now, ultimately, what our moderator is going to do, and the question is, what is this moderator? The moderator needs to absorb energy from these fast neutrons. Right? So they're going to take the energy and they're going to convert it into another form of energy. So I'm taking the energy that's associated, which is the kinetic energy of neutrons, their speed, and as I remove their speed, I'm going to convert it into another energy associated with the moderator, which is heat. Now, the nuclear reactors that we have in Canada are called CANDU nuclear reactors, right? This is a Canadian-made deuterium-uranium reactor, right? Deuterium is, this is deuterium down here. It's hydrogen that's heavy hydrogen. It's got an extra neutron in the nucleus. A normal hydrogen nucleus, a normal hydrogen nucleus has just a proton in the middle, right? Remember, it's got an atomic number of 1 and a mass of 1, 1.01, right? It's got a mass of 1, which means there are no neutrons there. This isotope here has a mass of 2. So not only is there a proton there, but I also have a neutron in the nucleus, which makes it a heavier nucleus, right? And if I use these hydrogens to make H2O, right, sometimes it's called D2O, but I'm not sure I really like that because deuterium is still hydrogen, right? It hasn't changed to another element. There is no D element, right? It's just a different isotope of hydrogen, right? But again, you might see D2O in some places. So this is the CANDU nuclear reactor, and like I said, it's probably the most popular, the most used nuclear reactor on the planet. I think I said this earlier in the course, that you'll find CANDU nuclear reactors in just about every country of the world. And everybody likes CANDU nuclear reactors because they work very, very well and they are terrifically safe. Now, it turns out the fuel that we use for a CANDU nuclear reactor is the standard uranium that comes out of the planet, which typically has a ratio of 99% uranium-238 to 1% uranium-235. Uranium-235 is the one that's going to be the unstable one that's going to absorb the neutron and have the ability to fission into, to release the energy that's present within them. So the moderator here is deuterium water, right? H2O using deuterium for hydrogen. And ultimately we can use other isotopes. Thorium is one element that we can use for a nuclear fuel. We can use uranium-233. We can use plutonium-239, right? So there are other fuels that we can use. But I think uranium-235 would be the most common one. Now, you think 1%, that's not very much fuel in this sample. Well, ultimately, that's more than enough for what we're trying to do, right? Now, if I enrich the uranium, have more than 1% uranium-235, we don't need that for our type of nuclear reactors, which is nice because this is the way most of the uranium comes out of the planet, right? So, but if we wanted to have the uranium that becomes more weapons-grade uranium, then we have to enrich it. We have to find a way to produce uranium that's got a higher percentage of uranium-235. And again, that's beyond the scope of this course. So we're just going to keep on going here. So when I look at what happens in a CANDU nuclear reactor, okay, so here is the nuclear core, the reactor core, right? And inside here, these 1, 2, 3, 4 are 4 fuel bundles. They contain the pellets of uranium, and around them is water, right? And this is the heavy water. This is the DH2O, the deuterium H2O, and it stays in this loop right here. Oops. It stays in this loop right here. And then it can go back through these 4 pipes, reconnects on this side, and it continues again. Now, what's going to happen is inside the reactor core, called the calandria, inside the reactor core, the fission is going to go on. So I've got my fission going on in the core, releasing thermal energy, releasing the neutrons with kinetic energy, which are going to be absorbed by the heavy water. The heavy water is going to pick up the thermal energy that's being released by the neutrons, and it's going to travel along this pipe as superheated water, right? And as it gets to this chamber, it's going to move through this pipe where it's going to transfer that energy to incoming cold water. So I've got water coming in here, right, from a source, usually a river or a lake. For all the ones that I'm thinking of in Canada, it's on a river. So we take water out of the river. The water comes in here. It goes into this chamber up here, absorbs the energy from the heavy water, which it's not mixing with, it's separate from, but it absorbs energy from the heavy water and turns into steam. The steam is under high pressure. Think about what happens why you don't leave a bottle of anything, a bottle of pop, in a car in the heat. It'll explode. The glass will actually explode because of the pressure. Well, as I create pressure here in this chamber, the steam actually pushes on turbines and it causes them to spin. And as they spin, it produces electric power. We'll talk all about that in chapters 16 and 17 and 18. We'll talk about how a generator works, how I make electricity, but ultimately the steam is going to get pushed up through this generator, just like wind going through a windmill. Right? The steam is under high pressure and it's going to cause the turbines in the generator to spin, and the steam will come out this end. Ultimately, probably will be cooled and get dumped back into the river. That's one of the problems here, is because the river's flowing this way towards a lake. It's pretty cold up here. By the time it gets to here, it's pretty hot. So if I compare the temperature of the water here to the temperature of the water down here, there can be a number of degrees differential between the two, and that messes with ecosystems downstream from the nuclear reactor. Okay, but again, that's a whole other issue of environmental damage caused by nuclear reactors. Okay, so there's the basic premise of a CANDU nuclear reactor. Now, I was reading about 3 Mile Island. 3 Mile Island had a problem. It's in New York State, and they have a nuclear reactor there. They had a meltdown of the core a number of years ago. Now, the Canadian nuclear reactors, the CANDU reactors, have got control rods that are up here, and they're pulled up. And if I ever need to slow this reaction down because the core is getting too hot, all I do is I release these 3 pistons, and they will drop back down into through the core itself, and it will act as an extreme moderator. So what it will do is it will absorb all the energy from all the neutrons and stop the fission reactions in their tracks. Right, so that's what the control rods are doing there, and it's a way, again, it's a safety mechanism to try and keep the core from overheating. So what happened at 3 Mile Island was the core overheated. They don't use deuterium in their nuclear reactors, so because of that, they just use plain water, and it doesn't absorb, it doesn't moderate nearly as well, so they actually use a higher grade of uranium in their reactors, and I think it's a little less predictable, a little less, it's a bit more spontaneous, which you don't want in a nuclear reactor. Right, so I'm going to use that superheated water that's coming out of the calandria, and I'm going to use that to push steam into the generator, which is going to make electricity. Right, and then the control rods that I was talking about a minute ago contain the element cadmium, which is a very good moderator, and it will absorb any free neutrons that are around, and it will stop that chain reaction in the event that we need to stop the reactor from doing what it's doing. So really, when we're talking nuclear energy for electricity, safety is always key. Now, probably the biggest single problem with nuclear reactors is a lot of the uranium that's in there as fuel, it won't undergo fission. So a lot of it, I'd say not a high percentage, but enough to leave a bunch of it left over. And what it does is it transmutates. It turns into another element, and the most common one is plutonium-239. So when the uranium-235s absorb their neutrons, right, they transmutate into plutonium-239, which is highly radioactive, just like the uranium-235, except plutonium is not a good fuel for the reactor, so it becomes a waste product from the reactor. The other problem with plutonium-239 is right here. Right? The half-life of plutonium-239 is in the thousands of years. The half-life, remember, for uranium-235 was only 1.5 years. Right? But for plutonium, it's in the order of thousands of years. So we've got all these reactors going on to Ontario, 5 I believe that belong to OPG. You can probably correct me if you've done your OPG assignment. And what they're doing is they are producing a lot of electricity. Again, maybe right now half the power in the province at this minute is being produced from nuclear power. And it's producing this plutonium-239. And we don't know what to do with it. Right? We can't use it. I shouldn't say we don't know what to do with it. We have no use for it. So what we're doing is we're making buckets of this stuff in our nuclear reactors because we're using this to make electricity. It's better than burning carbon dioxide, burning coal or nuclear or natural gas to make electricity, which both are creating carbon in the atmosphere and leading to global warming and climate change. So we have opted as a society to have more nuclear power, which means we're making more of this plutonium-239. And what we've opted to do is to try and find a way to store it somewhere until the day comes when maybe we can find a way to either make it into something less toxic, because I'd say it's probably one of the most toxic substances known to humanity. Right? It's nasty, 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 nasty stuff. So what we're doing is we're putting them in special drums. We're putting them actually in glass containers and then storing them in sealed drums, and then we're taking them to an old mine shaft, which is very deep in the Canadian Shield. It's about a mile underground, and we're taking these sealed drums and we're doing what humanity does. We're burying our problems. All right, so at this point in time, we've got caverns of underground storage units filling with plutonium-239 and other radioactive wastes, and we're hoping for the best. Probably not a great answer, probably not the most responsible answer, but we don't have a better answer at this point in time. So the world is not knowing about this, not paying attention to it, and we're just, like I said, just going about our lives and just ignoring the fact that we're making all this stuff. A lot of activists who have been quite active in lobbying the government against nuclear power for the last 50 years, since about the 1970s, have originally tried to alert the public to a lot of this stuff. But again, the government would say, what else are we going to do? You come up with a better answer, maybe we'll listen to you. So I think a lot of them have stopped raising a lot of fuss. So the other type of nuclear reaction is a fusion reaction, and it's the opposite of fission, where a fission reaction breaks an atom into smaller pieces. A fusion reaction joins two smaller atoms into a bigger atom. Right? Now, in order to cause two nuclei to fuse, they're going to repel each other. The positive nucleus of one atom is going to repel the positive nucleus of another atom. So there's no real way to push them close enough together for them to fuse unless you can get them moving fast enough. How do we do that? We heat them. So in order for this to happen, we need to get them to very high temperatures, similar to what happens on the sun. So fusion reactions happen on the sun, no problem, because they've got some temperatures on the sun that we don't quite have here on Earth, and because of that, fusion happens quite readily on the sun. Now, I downloaded this page as a summary, and it's a bit American, but that's okay. It compares fusion and fission in terms of what's going on. So what we're looking at here is using a deuterium hydrogen atom, H2, with a tritium hydrogen atom, H3, right? And I'm fusing them together to make a helium atom, which is 2 protons and 2 neutrons, and kicking out that extra neutron. And it says if I start with 1 kilogram of deuterium and tritium, I can make 676 units of electricity. What's a unit of electricity? It's how much the energy is used by the average North American person in 1 year. So 1 kilogram of fuel will basically be enough energy to meet the electricity needs of 676 people for an entire year. If I look at fusion uses the uranium-235, plus I'm going to use a neutron, which is slow, so it can be absorbed, right? It's going to cause the nucleus to fission or crack in the middle, kicking out, the 3 neutrons that we already talked about, right? And if I measure the amount of energy that comes from this, it says if I start with 1 kilogram of uranium-235, I will get enough electricity for 176 North Americans for an entire year. So you get a massive amount of energy. Now note that part of the problem here, part of the situation, if you look at the wastes and the fact that on this side we're making radioactive plutonium as a waste product, plus we're making other radioactive isotopes that are produced along the way, this is not a great answer, right? This starts with hydrogen and creates helium. Well, it turns out that the planet's running out of helium. We're using it for a lot of balloons, I guess. But the planet actually is truly running out of helium. So this wouldn't be a bad answer if we could actually have fusion happening. But again, remember, this needs to happen at temperatures close to the sun, and we haven't found a way to make that happen yet. Right? So the fission produces more energy than fusion. And this is also note the mass of the fission atom is huge, so fusion really produces much more energy per kilogram on this side than the fission does. Now, ultimately, we really want to find a way to make this work. There was a team a number of years ago, I think it was 1997, who thought they had found a way to make fusion happen. It was called cold fusion because it could happen at temperatures which were achievable here on Earth. But it turns out when all was said and done, even though they were on the front page of every newspaper on the planet for a week as saving the planet, it turns out that they had made some calculation errors and it didn't really work. So I think that was the end of their scientific careers. But we're still working on it. Okay, and like I said, if we can get it to work, ultimately maybe we can make some more helium for the planet. Now, we'll keep on going. I'm almost done here. One of the things that scientists discovered was, how do we generate enough heat to make fusion happen? Well, if I have a fission reaction happening, the fission actually produces enough heat for fusion to occur. So, if I take a fission reaction such as an atomic bomb, right, and I add deuterium to it, I can get fusion to happen, and the fusion itself will generate a huge, massive extra amount of energy. So it says where an average atomic bomb can produce as much energy as 100 kilotons of TNT, of explosive. Okay, and again, remember the hydrogen bomb ended World War II. If I add some lithium deuterides, which is basically lithium hydride, using the lithium hydride, using hydrogen 2, which is the deuterium hydrogen. If I add that to my atomic bomb, then these will actually fuse, right? They will fuse to make helium and release a massive more extra amount of energy, and I go from producing 100 kilotons of equivalent energy to 20 megatons of equivalent energy, right? 200 times more energy than the original atomic bomb that we were talking about. These are called hydrogen bombs because I'm fusing hydrogens together to make the extra energy that's going to be released by the fusion reaction. So we're really trying hard to find a way to produce electrical energy, to find a fusion reactor that we can use to make electricity. Right? And today we're using things called magnetic confinement fusion reactors. The textbook talks a little bit about them. Our textbook is pretty old, so they were still working on that when our textbook was written, probably about 12 years ago. It might even be more than 12 years ago. It might even be 17 years ago our book was written. So if you wanted to have a look at fusion reactors, you can see some of the things that they're doing, and it's quite interesting where nuclear fusion is at in 2020. Okay, the last topic in my course on nuclear power is looking at something that's not in our textbook. It's looking at nuclear medicine. Nuclear medicine, again, is where medicine is at in 2020. We spent the last 20 years working on nuclear medicine imaging and nuclear medicine treatments two things I can do with nuclear medicine with nuclear in medicine, right? One is for looking at the body and looking at what's going on, and the second is for treating things that are going on in the body. So I've left you with a YouTube video that I want you to watch. It's about 40 minutes long, and then there's a worksheet that goes with the video. I'm going to ask you